Hello. So today we're going to talk about chapter 13, which is titled Solids and Modern Materials. And don't forget, before we start, you'll want to make sure to have the printout of today's lecture notes. That's what it looks like right there, with our examples that we'll be going over. Plenty of space to show all your work. All right, let's talk about solids. Okay, so you may recall from Chemistry 1 that you talked about a crystal lattice structure. Um, So crystallography is an X-ray technique that's used to determine the arrangements of a crystalline solid. It's the reason why we know how these materials look at the molecular and atomic level. And so the smallest unit of this crystal lattice, so think of a lattice as just a repeating structure. As long as you have the atoms or molecules to bind together to make up that substance, it'll keep growing and growing and growing. So it's a lattice, it's not a specific molecule. So the smallest unit we call for this type of arrangement, a crystal, is called a unit cell. And that's what we'll be focusing on today, looking at the smallest item that makes up a crystal. And so it says here that unit cells are repeated over and over, right? So that's kind of what I was saying. It's like an atom is the smallest part of a pure substance made of atoms, like an atom of iron, and we're looking at a big chunk of iron metal and just trying to imagine it at that atomic level. Here we have something like quartz. Quartz is a crystal, but at the atomic level, we're looking for silicon dioxide molecules, but they're really arranged in an ordered way to make up that crystal structure. And so we're going to look at symmetry here as a focus today. Here are just a few examples of some sol crystals. So there's the quartz that I discussed just a moment ago. So you can see the color coding for each of the atoms or ions, depending on what we're looking at here. And then the macroscopic view, what we would normally see as the crystal. So just take a look at this image quickly and see how organized the atoms or ions are in these structures. All right, so different types of unit cells. Of course, we have many different ways that we can make one of these structures. We're going to be focusing on the cubic, and there's a few subtypes of cubic. The others are just here for your information. We won't be doing any investigation of types or calculations with these other types. We'll be sticking with the cubic. All right, so in general, the number of other particles, again, we could talk about these being atoms, they could be little molecules, they could be ions. So we're going to say just in general, particles. Um, so the number of other particles that each one is in contact with is called something called the coordination number. For ions, it's the number of oppositely charged ions that ion is in contact with. So it's roughly related to the charge of the ion. The higher coordination number means the more interaction. And so that's going to mean more interaction, stronger attractive forces holding that crystal together. And so I put a star next to that, as I think that's a main idea here for unit cells. So if we see a high coordination number, that's referring to how many contact points there are, and that would relate in a stronger attractive force for that crystal. So it's a way to compare. And then we have this other vocab term, packing efficiency. So this is a percentage of the volume and then what's occupied by those particles, be it atoms, ions, small molecules, etc. And so the higher the coordination number, the more efficiently the particles are packed together. So there's less empty space between them. They're just utilizing all of that volume of their particular unit cell type. So this is the most basic unit cell. It's a cubic unit cell. And this is just in general. Again, we're going to look at subtypes here in just a moment. So all unit cell corners are 90 degrees. You can see the picture there. It looks just like any cube that you've seen in geometry. The length of all the edges are equal. So we can see the picture down the bottom there. They've shown you a radius measured out and a length of a side. And it's just a perfect cube. They're all the same length. The three types that we're going to be looking at in this chapter are simple cubic, body-centered cubic, and face-centered cubic. And so we're assuming the unit cell is composed of spherical particles. The atom is mostly spherical, okay? And we can look at this as we've chopped this unit cell out of our entire crystal structure. So it looks kind of funny at first. You're like, where's the rest of those atoms? It appears to be chopped. Well, if we just cut that unit cell portion out, like a chunk out of the crystal, it's going to have portions of those neighboring atoms. So we'll be looking at those percentages, though when they're coming out as fractions here, same relationship, right? To be able to determine one type of cubic unit cell versus another and how we can calculate different properties of it. And so we'll say 1/8 of each corner particle is within the cube. Okay, half of each particle on a face is within a cube, and you'll see that in a second. This one does not have a particle on the face. And then 1/4 of each particle on an edge is within the cube. And so we'll look at this in more detail in just a second. We want to say that a face is one side of this cube. So this little square right here, or this square, or this square, each of those is a face. And so half of each particle on a face is within the cube. We're not seeing the half in this simple version, but you'll see it with the face-centered cubic. And then 1/8 of each corner. So 1/8 of each corner, that's 1/8 part of this entire atom that would take up that whole corner. We've chopped part of it away to isolate this unit cell. And so this little corner piece here, two-dimensionally, that is 1/8 of that material. 1/4 of it would be as if we counted two faces here. 1/8 and 1/8 would be 1/4. And so that would be 1/4 size of that entire atom that took up this space here. Okay. So this is just a graphic that allows you to see each of the types that we're going to focus on. Let me just move my camera for a moment so you can see that other, right here, that other heading here for this table. So we have the name of the cubic cell type, the atoms, the total atoms that make up that unit cell, the structure, and you see different pictures there. We have some different colors showing up in the more complex structures. We have that coordination number I introduced you to. The edge length in terms of r, meaning radius. So what is our length in terms of the radius? You can see we've got some square roots showing up here, so geometry coming in. And then we have the packing efficiency, which is that amount of volume that's occupied by the particles, not empty space. And so we could see the simple cubic there coming in at about half. And then the body-centered cubic, it's a little bit more involved there. We could see something in the very center there, that orange. And so we have more than half, 68% here. And then we have 3/4. I'll move my camera. Sorry if that's kind of weird. And so here we have 74%. Okay, so cubic unit cells, simple cubic. We're starting with the most basic type. We have 8 particles, one at each corner of the cube. So go ahead and take a minute, look at that purple image, and count how many particles represented by a sphere are there in this picture. And imagine it's got to be three-dimensional. Okay, so basically what we have here is 4 on this side facing you directly right there. If we looked at the edge on our right, we would see there are 4 here. Yes, I'm counting some twice, okay? But there's 4 on that side. There's 4 on this side up top. There's 4 on the bottom. Yeah, so, you know, how many unique particles we have? If we look at just this face, there are 4, and then behind it there's 4. We can look at it that way. Okay, 1/8 of each particle lies in the unit cell. That goes to that chopped picture of this that you're seeing here that I showed on a previous slide. And so each particle is part of 8 cells. The total 1 particle in each unit cell. And so this is going to get, you know, kind of confusing with the fractions and how we're then combining them to get whole numbers of atoms again. Just stick with me. I do have a review YouTube video that's within this PowerPoint. I'll make sure to put up the PowerPoint so you could click on that video after seeing it here. And then that way you can revisit it and it shows the animation that helps with the description. So we see that we have the edge is twice the radius, so it's pretty equal there, and the coordination number would be 6. Okay, so here's a nice image, that cutaway again, nice and large, so we can get a look at it. And so we see the length, if we define that as L, the radius would be half of that length, so we're defining that as R. And so if I get 2 R's, that's going to equal 1 length, okay, for a simple cubic. And so this is another image that's in the textbook, and it shows our coordination number. Why is it 6? Well, it's highlighted 1 unit cell in the top right here, and then you could see all the other atoms that it would be in contact with to get that coordination number. And then we've taken out, again, that piece of 1 unit cell for simple cubic. And you could see kind of the shadowed cube that we've sectioned out so that you could see, excuse me, how those atoms are spheres, but we're taking this little chunk out that is making up what we call a unit cell. And so we could see how many atoms per unit cell. If we're getting an eighth of each of these atoms, then if we add those all up, there's 8 corners, and so we'd get 1 full cell. Even though it's not a complete cell, it's combining all of the pieces that make up that unit cell. Okay. All right. So here's a body-centered cubic, and you can see that we've shoved another particle in the center there, that orange part, and then the purple particles have kind of spread out a bit. They're not completely touching. Okay, so here we have 9 particles. We had the 8 from before, and we've shoved that one in the middle. We have an eighth of each corner lying in the unit cell, just as before. But we're going to say that there are 2 particles in each unit cell, where the previous, the simple cubic, only had 1. Where are we getting that? We're getting those 8 corners that we originally had in the simple cubic, because those purple spheres are still there. But we've got that 1 additional particle in the center. So that added is going to give us 2. 1 here and 1 here. The edge of the unit cell, again, that length edge is going to be equal to 4 divided by square root of 3 times the radius. Okay, and the coordination number for this particle is going to be 8. Here's the image again from the textbook, where you can see the larger unit structure for this particular chemical with the structure here, and you can see our unit cell is shaded darker to show you how they arrive at the coordination number of 8. So it's how they're interacting with the neighboring particles of the larger structure. And then again, how we've looked at the picture from the previous slide, and we're slicing out that unit cell. And so we have the 8 1/8 corner on each side, and then the 1 atom in the center to give us 2 total atoms per body-centered cubic unit cell. All right, here's example 1 on your student note sheet. So let's talk this through together. A body-centered cubic unit cell, which is what we just saw, has a volume given of 4.32 times 10 to the negative 23 cubic centimeters. Find the radius in picometers. Okay, so again, we're talking about atoms, right? So we're using atom sizing. If we're saying the volume is cubic centimeters, well, that's a macro scale. We can measure that with a ruler. But we're looking at the radius of an atom within that volume. Centimeters way too large. So we're going to go down to the picometer here. So here's how we would solve that. Of course, we're going to line up what's given in the problem with its variables so that we can think about relationships between them. And so what we've done here is we've said, okay, the volume was given. We have that large number there. And then the radius, we just made that note that we want to make sure it's converted into picometers from the centimeters of our volume. So here's our game plan. This is how it's outlined in the textbook, which is really nice because they combine the formulas with a visual too. So it's a nice layout. And so that we're going from volume to length, knowing that volume is calculated as length times width times height for solids. So knowing that relationship, a length cubed gives us our volume. So that's where that relationship's coming from. So we're just going to take that backwards to get the length. And then we're going to go from the length to the radius by using the relationship for this particular unit cell. And so that we were told this was a body-centered. And so you'll recall from that slide of body-centered that the radius is given as this relationship here to the length. So 4 times the radius divided by the square root of 3. So it looks messy, but we'll just kind of plug in numbers and follow it through. So here's what we end up doing. So what we've done up here is we've just said, okay, here's the relationships used, volume formula, and then the edge length for the body-centered cubic. Okay, so again, we're going to take our volume that was given, and we're going to take the cubed root of it to undo this cube and isolate what just one length would be. And so we get that here after doing the cubed root of our volume. Okay, and so then we need to find out the radius from there. So we've just found L. Okay, we're going to rearrange this formula so that we could plug in L and solve for R. So in doing that, we're going to undo the multiplication here. And so that's why we see division by 4 on this side. And we've carried the R over to the other side of the equation that way. We've brought our length over to the opposite side of the equation as well, and this is how it would be organized. So our square root 3 was in the original formula for body-centered cubic length. That is here. But from rearranging this formula algebraically to solve for R, we have our length that we've calculated now being multiplied by that square root of 3. And then we're going to be dividing by 4. So in a sense, this is a repeating formula that we could use going forward for finding the radius of a body-centered cubic. So if you wanted to put that up in the equations box on your note sheet, you can do that, and then just instead of putting this number in that's in parentheses, that's specific to this problem, you could just put L. So that when you calculate the L, you would multiply it by square root of 3, divide it by 4, and that would mean your radius for this type of cubic only. Okay, so when we do that math here for this problem, we end up with this large number here, but that's again in centimeters. So we need the relationship to go from centimeters to picometers, and what we need to do for that is we need to go through the meter. And so using the relationship there, a centimeter is 1/100th of a meter, or 0.01. And so we have the centimeters on bottom to cancel. We're left with meters. We want picometers. And so the relationship there is that it's really small. A picometer is 10 to the negative 12th of 1 meter. So we arrange that appropriately to cancel our meters out, be left with picometers, and we get 152. Now, another good practice is to check that your answer makes sense. And so they have a check here. The units of the answer in picometers are correct. The magnitude, the 152, is reasonable because the atomic radii range roughly from 50 to 200 picometers. So just, doing a Google search and finding what the typical radius is of an atom. It's going to vary with what atom you're looking at, but they're giving us a pretty big range here of 50 to 200. And so the 152 is within that range. This is a probable answer. Okay, so it makes sense. All right, let's talk about face-centered. So face-centered is the most complex that we will be looking at in this course. And so we have 14 particles now. It's more things in there in this unit cell for this type. We have one at the center of each face. So a face is a complete side. Okay, so if we just kind of look at this left side here, we could see the orange. We have a half of a sphere right here. Here's a different half. There's one on the bottom face, okay, kind of like an upside down bowl here. And then here we have a right side up bowl on the top. And of course we have two faces that we can't see from this angle of how this cube is pointed towards us. So we've got, it's 6 faces and each has a half. That's the orange, right? That's half the sphere. So that's what we're seeing here. And of course the 8 corners are still the purple. We still have 1/8 of each atom that is represented by those purples. And what we need to do here to figure this out is a little bit of kind of quadratic formula here. And so we'll be seeing that in an example in just a minute. We have the edge of our unit cell as defined as 2 square root of 2. That's our edge, which is our length. All right, times the radius of the particle. Okay, so 2 to the square root of 2r. And the coordination number here is 12. So it's in contact with 12 other particles. And so here again, we see the image that's similar to the other two types from the textbook, where we have that highlighted corner of where we're taking our sample to get a 1 unit cell. And so this shows the coordination number, all the interactions, there are 12. And then we have our unit cell that we saw on the previous page with that shadowed cube that we're going to section out of the center just to see the particles that make up that smallest unit of our crystal, the unit cell. And so in this case, we have our 1/8 again from each corner, but then a half of an atom of every 6 face. If we add those together, we get 4 total atoms represented in a face-centered cubic unit cell. So here's example 2. Just a simple question. How many atoms are there in the unit cell of a face-centered cubic structure? All right, so the answer there is 4. And here's where I was mentioning earlier, there's a review video that I found on YouTube. It's a minute or so long, and it goes through each type, but it animates, so that might help you kind of visualize this a little better. And so I invite you to take a look at the PowerPoint that I upload after this video, and you'll be able to click on this and view that at that time. Okay, here's example 3. So the edge length of the unit cell of tantalum is 330.6 picometers. The unit cell is a body-centered cubic. Tantalum has a density of 16.69 grams per cubic centimeter. 2 parts. Calculate the mass of one of the atoms, and then calculate the atomic weight of this element in grams per mole. And we can do that just from the information they've given us here. Notice that in the previous examples, as well as this one, they're telling us the type of unit cell structure that has to be given, because as you know, they each have their own arrangement, and so they're each going to have variables regarding length and radius, and so how many atoms combine it. So they have to give us what type it is. And so what else are we given here? We're given the length now in picometers, and we're given a density. Okay, so let's see what we can do with this. All right, looks like a lot of steps, but let's just go through each one. So the first thing we did was, we're going backwards from a previous example where we went from centimeters to picometers, right? We were given picometers, but now we want to go the opposite direction and go larger scale. So we're going to be doing it backwards. We're going to be going from picometers and converting it into centimeters. So we have the same relationships here, and all we're doing is moving a decimal point, okay, to get to centimeters. And so now we have calculate the volume. So this is our length in centimeters. So length times width times height, or cubing, we get this value here. Okay. Calculate the mass of the 2 atoms in the body-centered cubic. So we have 2 atoms that make up a body-centered. Again, one coming from the 1/8 of the 8 corners. So 8 1/8 equals 1. And then the 1 atom from the center. So that's 2 atoms total because of its body-centered type. And so we want to calculate that. And so we have our density as given. We have our volume. And so from there, we get our mass just by manipulating the density formula, okay, solving for mass. So now we have grams. And so that's for 2 atoms, though, because of its body-centered cubic structure. So to get 1 atom's mass, we need to divide this by 2. And that's what's done here in step 4. Okay, so we still have a rather small number. Uh, and so now we need the atomic weight. So Avogadro's number makes an appearance. Okay. And so what we're going to do here is we're going to take our mass in grams of one atom and divide it by Avogadro's number, and that way we will get grams per 1 mole of that substance. And here we are, 181.6 grams per mole. Now we could take this one step further and just validate that on the periodic table, but just remember that masses are not the best to identify an element because the periodic table is showing you an average atomic mass based on how many different isotopes there are for that element, which it varies per each element, and then the weighted masses by those number of isotopes. So the 181.6, you should be able to get, close to where tantalum is on the periodic table, but it may not exactly match because it's really an average on the periodic table. Okay, so we're going to classify other crystal solids. There are other types. So we have a molecular solid, which are solids that are made up of molecules. Okay, ionic solids, they are made of ions. And atomic solids, we have three different sub-levels of atomic solids. Okay, so just based on atoms, we have non-bonding. They're held together by dispersion forces. Okay, remember from the last lecture, the dispersion forces are present in every type of interaction with atoms. So diatomics, the two atoms are being held together by dispersion. Remember, it's a very temporary partial dipole, and it's just because the electrons are constantly moving around those atoms. We have metallic, and so we have metallic bonds. We'll go and review that. And then we have network covalent, which are covalent bonds. So this is just a chart from the textbook that breaks down each type just in a tabular format, kind of like a flow chart, and shows some examples of substances that would fall in that type. So feel free to pause the video. Excuse me, feel free to pause the video and just take a closer look at this image. But we're going to keep moving. So let's talk about the molecular solids first. So this is where the lattice sites are occupied by molecules. So I just gave 3 examples of molecules. It doesn't have to be these 3. We've got carbon dioxide, water, and table sugar there. The molecules are held together by intermolecular attractive forces, which include the dispersion or London dispersion forces, the dipole-dipole interactions, and hydrogen bonding. So molecular solids have the weakest attractive force. So if the forces are weak, it doesn't take much energy to break them. And if it doesn't take much energy to break them, we can melt them with just a little bit of heat. So we see weak attractive forces resulting in a low melting point temperature for these substances. Okay, let's compare 2 other molecular solids. Here we have the 2 cyclic compounds. We have benzene, and you see its formula there, and then we have toluene. The structures look very similar to each other. Can you notice the difference? All right, so let's take a look. If you looked at both structures and you saw that up here there is a CH3 bonded to this top carbon of the ring, whereas in benzene there's just a hydrogen, you found the difference. Okay, so it's very subtle. And we have our molar masses just reflect that additional CH3. Okay, they're both made up of dispersion forces. And let's take a look at the melting points. The melting points of the solid are low, right? Toluene is very low, all right, less than 0 centigrade. So that's comparing just 2 of thousands of molecular compounds. Okay, and this image I grabbed just to kind of show you benzene. You're probably not familiar with it. It's just used as a solvent in chemistry. It really doesn't have any industrial use. But if we freeze it, it just looks like ice. You can see in that picture, it's a clear solid. Okay, but then I liked this image because it showed the crystal structure. So you can see that ring that is characteristic of benzene. The carbons are all that gray, and the white are hydrogen, just as we saw in a previous video with my model kit, right? The white are always hydrogen and the black are carbon. So we're seeing that same thing here. It's kind of a universal coding for molecules so that you can understand without the lettering of each element. It just makes it too cluttered. So the cleaner we can make the images to understand what's going on, the better. And so this is showing a unit cell, and we have our benzenes in place within that unit cell. Okay, so ionic solids. So this is another type. So we have the lattice sites occupied by ions. They're held together by Coulombic forces. If you recall Coulomb's law from Chem 1, if not, we'll review it very quickly here. And the Coulombic forces are much stronger than dispersion. And so we have high melting points for these substances. All right, so here's our review. So we have a unit cell representation here of sodium chloride, well, more of a crystal structure, it's much larger, right? But then off to the right, you could see the strong electrostatic force. So our positive and negative ions, remember the negative ions are larger because they have that extra electron cloud where the cations have lost electrons to become an ion, and so they're smaller with the loss of an electron cloud from losing those valence electrons. Okay, and so this is a review of Coulomb's law. Basically, Coulomb's law is relating the distance between particles and their attractive force. So basically, the closer particles are, the more attracted they are to each other. And the top line there, you see two positive signs, like charges repel. That's basically Coulomb's law. Okay, and our last subtype here for covalent, we have metallic bonding. So metals are unique in this type of bonding, where the metal atoms, you see there in the picture on the left, are in blue. They're arranged in a very ordered arrangement, which we would know for a solid. We would expect to see that. But then we have this, quote, sea of mobile electrons. So you may recall from learning this in Chem 1, that was the way to identify it in multiple choice, right? It's metallic bonding if it says sea of electrons. So that's typical wording for metallic bonding. And what does that mean? If you want to see an animation of that, go ahead and click the video that I've posted here on this slide, and it'll take you to a YouTube video to just help you visualize this in motion, okay? The fixed sea of, the fixed atoms in the sea of electrons. All right, so let's review our atomic solids. We have quite a list. So we have non-bonding. They're not physically bonded with a chemical bond. They're just associating next to each other. So that's that dispersion force. That's our weakest force. So because it's weak, they're going to have low melting points. And this would be examples of noble gases in their solid form. So do you remember the noble gases? That's our group 8A. And so if we had a solid form of helium, neon, argon, krypton, xenon, and so on, that would be this type of atomic solid. We have the metallic atomic solids, which are held together by metallic bonding. The melting points are going to be variable depending on the material, so we can't really make a for sure statement on whether it's high, low, or in the middle. It's just going to be varying high, low. They form the closest packed crystal structures, so that's kind of unique to it. And then we had our network covalent. So that was the covalent bonding, which is the equal sharing, right? So like my water, covalent bonds, okay? The structure is restricted by the geometry of the bonds. So back to my water molecule, the water molecule has a geometry of 120 degrees for this bond angle. And so, like that, or if I go back to my tetrahedral of 109.5 for each bond angle, it's going to be restricted by that because of those bonds. And so very high melting points because you need to agitate those bonds to get the substance to go into a liquid, right? We're not breaking the bonds because if I break this bond, I no longer have water, right? I have a hydrogen ion and I have a hydroxide. We're not breaking the bond, so it's staying water, but we're just giving it more energy, right? To go from those phase changes. All right, so here's just an image showing you a couple different metals and what they look like. So we have a sample of nickel and zinc, and then showing you if we were to zoom in to see how the metals are very closely packed. That's what this image is showing to us here. All right, so example 4. Which solid would you expect to have the highest melting point? We have magnesium oxide, we have a diatomic iodine, and we have krypton. Okay, if you guessed the ionic solid magnesium oxide, you are correct. All right, so just identifying the bonding type is the way to answer this question. It's not more complicated than that. So noting that magnesium oxide is made up of a cation, magnesium, and an anion, the oxygen. That right there defines it as ionic. Ionics have the highest melting point. Okay, what's the difference between the other two? We have the diatomic iodine, so that would be a dispersion force, and the krypton, our noble gas here, would be a dispersion force as well. Which are the weakest, right? Okay, network covalent atomic solids, and let's look at carbon. Okay, carbon comes in two forms, graphite and diamond. Okay, if you're writing with a pencil right now for your notes, or you write with pencils now and then, that's not lead, as a lot of folks call it. Okay, it used to be lead many, many, many years ago. I've never seen lead pencils. Okay, so it's been a while. This is now graphite. Okay, what are some properties of graphite? Graphite is very brittle, so I can take my notes here and just apply some pressure. Whoops, I stabbed myself. On a hard surface, it would be better. And if you push hard enough, you'll get some dust from that graphite, and you'll see that it is rather brittle. Whereas diamond, is one of the strongest substances that we know of. So they're quite a contrast there with strength. Okay, in graphite, the carbon atoms are in a sheet, so we'll see an image of that in a moment. It's similar to benzene in that it's a 6-member ring. The bond length is 142 picometers. You do not need to memorize that. It's an sp2 hybridization, so for each carbon, the way it's arranged, let me see if I have an example here. Yes, in this molecule, my ethene molecule, my propene molecule, propene, the double bond. So this carbon would be sp1, p2. Remember that hybridization comes from the bonding regions. And so this double bond counting as one region, sp1, p2. And so this carbon atom here has an sp2 hybridization. Okay. We have each carbon has 3 sigma bonds and 1 pi bond. So reviewing that, remember that the sigma bonds are single, sigma signal, and then the double bonds are made up of 1 sigma and 1 pi. So when we have that, it's a trigonal planar geometry. Each sheet is one giant molecule. The sheets are stacked and held together by dispersion forces. Okay, they're weak, and the sheets are 341 picometers apart. Okay. So this is an image that shows you those sheets. So you can see them coming across horizontally, and then the blue dashes showing you where we can see those dispersion forces that are just holding them just close enough to maintain that solid structure. And we see a chunk of graphite underneath. And if you want, you can compare that by looking very closely at your pencil tip, and you'll still see that shine and kind of striation that you see in this image. Same substance. Okay, high melting point. So almost 4,000 degrees centigrade, which is super, super hot to melt this guy. There is some covalent bonding, right? Carbon to carbon covalent bonding. It's a slippery feel. Because there's only dispersion forces holding the sheets together, they can glide past each other, and this is what also makes it brittle. So when you break something, you're taking those two sheets and you're breaking the dispersion forces, and they're sliding past, and so that's how you're getting pieces of the graphite to separate. They're used as lubricants in addition to our pencils. They're pretty good at conducting electricity, and they're very good at insulating, keeping heat. But they're chemically non-reactive, right? Just carbon. Our diamond is a much more ordered and contained looking structure than just sheets. Each of our carbon atoms here would be sp3 hybridization, so um, that would be like my tetrahedral here, ignore the chlorine. But if we have this carbon atom, we have S, P1, P2, P3. So it's tetrahedral geometry, sp3 hybridization. It effectively makes each crystal one giant molecule held together by those covalent bonds, and you can follow a path from any atom to another atom. So let's take a look at that. So here we are, huge network of carbon atoms bonded to each other. You can follow here. We don't have those blue dashes that were representing the dispersion forces of the graphite here. Here we see the kind of white or silvery bonds, just like my model kit. They're a light gray color to represent that physical connection, that covalent bond. Okay, very high melting point here as well. We have almost 4,000 degrees centigrade here. They're very rigid because of the directionality, so they mean the bond angles, right? This is a very rigid looking structure. And so because of these bond angles, it's hard to compress. Okay, if we were to compress like these two hydrogen atoms, what's going to happen? Two hydrogens, they're going to repel, right? Because they're both plus. So it's rigid in that the charges are just, I don't want to use the word dispersed, but the charges are, spread out in a way so that the like charges have a maximum distance from each other. And so that contributes to a rigid structure. These are used as abrasives. Some material science, you'll use diamond to cut other materials because it's one of the hardest substances we know. It will insulate electricity, it will not conduct it. Excuse me, but it is a thermal conductor, one of the best known to transfer heat, and it's non-reactive as well. The carbon atoms all satisfied with their bonds just like with graphite, so not going to react with much. So that brings us to example 5. High pressure favors the formation of diamond from graphite. Probably heard that, right? What can you conclude about the relative density of the two substances? Well, looking at these choices, we can tell that if high pressure, right, a squeeze, high pressure favors the formation of the diamond. So the diamond must be more dense than graphite. It can stand that high pressure. Graphite, if I put high pressure on it, it's going to slide and it's going to break. But the diamond must be more dense. We saw those particles here closer together. Here's our diamond, okay? And then if I go back, here's our graphite. You can see much greater distance between those sheets of carbon atoms here versus the diamond structure where they're all interconnected with those covalent bonds, okay? So there's our response for number 5. Okay, so this is the material part of the chapter where we're looking at more modern materials that have come about. So Buckminster fluorine and nanotubes. These were different forms of carbon. Carbon is pretty special because of how it forms bonds and it pretty much gets along with a lot of different atoms. That's why there's a whole class after Chem 2 called organic chemistry, and we've actually broken that down into 2 semesters, right? Organic 1, organic 2, and it just focuses on the bonds and reactions of carbons. Okay, so that's how many different ways we can look at carbon. There's a whole class on it, right? So the Buckminster fluorine was discovered in the 1980s, which is recent in chemistry history standards. It looks like a soccer ball. Maybe you've seen that before. There's 60 carbon atoms. They're called fluorines or buckyballs as kind of a shorthand. Okay, a nanotube, you may have heard of this too. A lot of them are coming out in medicine, being used for medicinal purposes, and some material science forms as well. We'll take a look at an image in just a minute that shows different uses for these. They're single-walled tubes, but so if you imagine like a straw where it's hollow in the middle, but the outside is like that sheet of graphite almost, where it's just rounded to make a straw, that's like a nanotube, okay? If they're multi-walled, there'll be rings one inside the other. So very complex looking structure, okay? This is the buckyball that we see here, carbon 60. It looks like a soccer ball, right? It even has the diamond print sides there where you can imagine every other one being colored as black or white, right, to make up that soccer ball. We have a single walled nanotube up on the top right here. So it looks like kind of like a chain link fence, but just rolled up. And so if we were to zoom in on this image, you'd see that hexagon structure that we have in the buckyball. It's just shrunk down for this image to show you the linkage of how we can make a tube from it. Okay, here we have a multi-walled nanotube, and they've used different colors to show those different layers, but these would be one fitting inside the other. Okay, here's a graphene nano ribbon. Okay, and then we have a graphene sheet. So just kind of showing perspective there of it being just a long one-dimensional surface. Okay, this image is from a website called Compound Interest. You can see it at the very bottom of the picture there. I made this into a link that if you click it, it'll blow it up and it'll bring you to that website. And it's basically a really cool website with all kinds of graphic images like this, where it's like a shortcut kind of overview of different substances and different processes, and it tends to focus on chemistry. So it's a really cool website. If you got some time to check it out, really easy to read information on different substances. And here's our nanomaterials. So this is just a short list of the application of where we've seen nanotubes currently. Okay, again, only been around since the 80s, which is still recent. May not be recent to you, but it is recent in chemistry history standards, right? So used in things like energy, okay, biology, tools made of carbon, high density carbon. We have materials, carbon fiber, okay? It's a very hard substance, but it's super light. So things like the helmet you see there could be made in carbon fiber. Cars, materials, race cars are starting to be made as carbon fiber because it's very strong material that hopefully doesn't break when it crashes. And if it does, it's easy enough to just replace parts by connecting them, as panels. And electronics. So your flexible displays, if you have a folding phone where it is a smartphone, the fact that that display can fold is due to nanotubes. Okay? And agriculture, right? So you could take a look there. We have a sensor, we have a pesticide thing there. And so lots of applications, okay? The last two examples here, we're going back to the beginning topics of the chapter. I wanted to give you two more examples of how questions could be asked to not only help you with the homework, but to help you prepare for our quiz. So here's another example of what we can calculate with cubic structure. So we have nickel, crystallizes in a face-centered cubic, so we're told the type. If the density of the metal is given as 8.908 grams per cubic centimeter, what is the unit cell edge length in picometers? And so I'm reminding you on this slide what that face-centered cubic structure is again. So we can see there are 4 atoms per every unit cell for this type and where that 4 is calculated from. Again, this is our most complex unit cell structure that we're studying in this course. So this is our nickel sample here. How would we solve this? We're given density, we need the edge length. Well, we're given density, what is that? That's giving me a mass and a volume. And so we're going to use that information like we did in a previous example. We're going to divide by Avogadro's number and get how many grams per atom, right? Because grams per mole is not helping us with a cubic lattice because that's by just a few atoms, right? A mole is Avogadro's number of atoms. Too many. So we're going to divide it by that and get how many grams per one atom. Then we're going to calculate the mass of 4 nickel atoms because that face-centered cubic is made up of 4 atoms. Okay, go back to the previous image to see that. So we're going to divide it. You can see I put my units there, how many atoms in a unit cell. There are 4. And so now I have grams per unit cell. And from there, we can bring our density of our grams per unit cell, our grams per unit cell, and then divide that by our density. And now we've given a volume. So now we have our volume of our unit cell. Are we done with the problem? No, because we don't want the volume, we want the edge length. But we're almost there because we know that the volume is length times width times height. And so all we need to do is divide this volume by 3. Now we have the length of our edge, but it's in centimeters. So what we need to do for our last step is we need to convert centimeters into picometers. And so you'll get used to doing this with this relationship. A centimeter is 1/100th or 10 to the negative 2 meters. And then our picometer is 10 to the negative 12 meters. And so from there, we can relate picometer directly to centimeter. Or if you go back to the beginning of the notes, you'll see how I did this in 2 steps, going through the meter. And we arrive at 352.4 picometers for our edge length of our nickel face-centered cubic unit cell. One more. Example 7. Let's take a look. A certain temperature and pressure of an element has a simple body centered cubic unit cell. The corresponding density is given, and the atomic radius is given. We haven't been working with radius. Remember, that's our unit for radius, right? Calculate the atomic mass, and we're told in AMU, atomic mass unit, not grams, the atomic mass, okay? Atomic mass unit for this element. And I'm actually going to take it a step further at the end of this problem, and we're going to use that atomic mass to best approximate. Remember, it's not the most accurate to go by mass to identify an element, but we can use that to get within 1 or 2 different elements that this could be, okay, by looking at the periodic table at the end. So let's take a look, okay? So first we have to convert into centimeters. And so this is our angstrom unit, which is our smallest unit we use to describe atoms. So our radius in angstroms, we need to convert to centimeters. Well, this is just moving the decimal place several places to the left. And then you see scientific notation there, it's 10 to the negative 8. Okay. But now we're going to use the Pythagorean theorem, because this was our radius. So that's half our length, okay? And so what I did here for you guys is I put a reminder of the Pythagorean theorem, okay? Now, in math class, when you first learned this, I'm sure you said to yourself, I'm never going to use this in real life. Well, here we are. Chemistry 2, we see the Pythagorean theorem come with a vengeance, and here we're going to be using it. And so translating the Pythagorean theorem, a squared being one edge, b squared being another edge, and c squared being this hypotenuse of our triangle, take a look at the image here of our face-centered cubic. Okay, we can look at an edge on the bottom, an edge up the side, and we have our radius going connecting the 2 points. And so from here, we can translate that to edge squared instead of a squared. Edge squared, meaning this edge, instead of b. And then 4 times radius here are c squared. That's just what's given in the face-centered cubic arrangement. Square that. Come down. And once we simplify it, we see the 2 square root of 2 times the radius, or 2 square root 2r. Okay? And so that's the derivation of that. Okay? So we can plug in here using this base formula, which is derived from the Pythagorean theorem. We want to find d. We're given our radius. We're going to plug it in right here. Okay. We're going to simplify, and we're going to get one edge as this number here, 4.11 times 10 to the negative 8. Again, we're still in centimeters because we converted angstroms to centimeters. We're still working in centimeters. Okay, that's okay. We got one length, so we're going to calculate volume now. Length times width times height, or just cubing this number. So here's the cubing, and we get this value, 6.95 times 10 to the negative 23 cubic centimeters. Are we done? No, because we weren't asked to calculate volume. So here we have the rest. So we have volume, we were given a density, we can multiply those two together in a way to cancel out the cubic centimeters, and then we'd be left with grams. So now we have the mass of our unit cell. We're going to now use the fact that in a face-centered cubic, we've got two atoms that are going to be called X for that type of center, and so that's going to be equal to Avogadro's number. We take our mass that we just had solved for, and from here we can arrive at grams per mole, okay, by dividing them here, and we get 88.95 grams per mole, which is just converted over to AMU, right? Remember the periodic table, if we're talking about a single atom, we would say its mass is atomic mass units. But if we're talking about moles, it's now the same value on the periodic table, but in grams. So it has that direct relationship. And so then I took that extra step here, something that you could see, and said, okay, where on the periodic table am I closest to a mass of 88.95? And the closest I found was yttrium, which you could see underneath the 39 here. It says it has a mass of 88.906. So that was the closest match. It's most likely that this was an example of yttrium. And that's chapter 13. So now that you're done watching this video, go ahead and try homework number 5. And then I'll see you next time for a quiz.